Students, in today's class we will be discussing about leakage currents. So what are leakage currents? They are also called as what? Reverse saturation current, isn't it? They are also called as what? Reverse saturation current. We have discussed this in our previous class in first year, isn't it? So reverse saturation current we call the leakage currents as. What are they? They are the currents, or leakage current is what? It is the current which will be flowing through your PN junction when that PN junction is reverse biased, isn't it? So when the PN junction is reverse biased, we will have a small current which will be flowing. Actually, when the PN junction is reverse biased, it is like open circuit, isn't it? So it is like the device or the diode or the junction is said to be off because in the depletion region bit will increase, and there happens to be no off, like there won't be any flow of majority charge carriers, and there won't be any current which will be flowing, isn't it? So now after because of this reverse bias applied over there will be minority charge carriers in your P region and N region. This turns to move because of the reverse bias applied to the junction, and because of those minority charge carriers, so there exists a small current. So there exists a small current which will be flowing through the junction. So that is called as what? Reverse saturation current or leakage current. Or leakage current is called as what? The current through the reverse biased junction or reverse biased transistor junction, and it is a small current. It is all because of the minority charge carriers. Okay, so now I can say the total current through a transistor, what I see total, will be equal to what? The majority charge carriers current. So that will be that. Okay, so that will be a huge current, and plus minority charge carriers also will make a small amount of current which is actually negligible. But to calculate or to measure the total current, I should consider the minority charge carriers or leakage currents too. Okay, because your BJT is called as what? Your BJT or your normal transistor. Bipolar junction transistor will call it as, isn't it? From normal transistor, bipolar junction transistor will call it as what? BJT, bipolar junction transistor. What it is? It is bipolar. Bipolar is what? What is unipolar device? What is bipolar device? In unipolar devices like your FET, what it is? So the total current which will be flowing through the device is all because of the majority charge carriers. Only one charge carrier will make the total current in that particular device. So they are called as what? Unipolar devices. Now these are what? Bipolar devices. Bipolar devices means what? So here we have the majority charge carriers plus the minority charge carriers. Leakage current will make the total current IC. Okay, the total current of the device. Okay, so IC total will be equal to what? IC majority charge carriers, the maximum huge current plus the very small current which will be there. Okay, so this is how I can make out the total current of your transistor. Okay, so now we will be talking about the two of the leakage currents which will be there for different combination of your transistors. Okay, so first we will consider the collector to base leakage current, that is called as what? ICBO. This two of these things are very important. They may ask you to define ICBO or ICEO. They may ask you to define. Okay, so for 1 mark. So collector to base leakage current, it is called as ICBO, collector to base leakage current. Okay, ICBO we call it as. So this is, so ICBO is the thing, but it is the collector current which will be flowing. It is the collector current which will be flowing through the device when this IE or that emitter terminal is open. Okay, so when we open circuit or when we open the emitter terminal, and will be providing certain voltage VCC across your collector to base. So then the collector current which flows in this circuit is called as what? IC will be equal to what? ICBO. So this is what? It is collector to base leakage current. So it is collector to base leakage current. So this is what is called ICBO. So when this emitter terminal is open, when emitter terminal is open, IE will be equal to 0, isn't it? So now the current, when now a small current flows through the device, so this current is called as what? Your ICBO, or a collector to base leakage current. So this current is not because of the minority charge carriers it should be flowing. Okay, is that okay? So when we have this emitter terminal open, there exists a small current, or because of minority charge carriers, that is what is called ICBO. Okay, so it is the collector current which flows through the circuit when this emitter terminal is what? Open. Okay, so this is what is what? ICBO. Okay, so then ICBO depends on temperature and reverse bias voltage. Okay, so for when we have ICBO has a dependency with temperature and also with the reverse bias voltage. So firstly we consider temperature. Okay, so when we have this temperature increase, we know that semiconductors they will conduct more and more when the temperature is increased. More and more charge carriers, more and more electrons will be liberated, isn't it or not? Okay, so more and more electrons starts flowing when we increase the temperature, isn't it? So here the temperature dependency is very important. For every 10 degree rise in temperature, for every 10 degree rise in temperature, so the leakage current doubles. Okay, so the leakage current doubles for every 10 degree centigrade or 10 degree rise of temperature. We have this ICBO doubling. Okay, so ICBO or the leakage current doubles for every 10 degree increase of the temperature. Okay, so this is how we have the temperature dependency and the reverse bias voltage. As I increase this reverse bias voltage more and more, your ICBO means your leakage current will be more, so that people are aware of it. Isn't it or not? Okay, so this reverse bias or this reverse bias voltage, if I increase more and more, so ICBO will be more and more. Okay, so more leakage current will be flowing. Okay, so that is the dependency of your ICBO with reverse bias voltage and the temperature. Okay, so now coming to collector to emitter leakage current. What it is? Collector to emitter leakage current is called ICEO. Collector to emitter leakage current, what is called ICEO. Okay, so now here I have considered this configuration wherein we have this base terminal open. So what it is? It is your collector current which will be, or it is the collector current which will be flowing through the circuit when your base terminal is open circuit. When the base terminal is open circuit, we have some leakage current which will be flowing. So that current is called ICEO. ICEO, collector to emitter leakage current, we call it as. Here base terminal is open, that's why IB will be equal to 0, and we have a reverse bias made over here, and because of this reverse bias, a small current will flow because of the minority charge carriers. That is called as what? ICEO. ICEO is nothing but what? It is the collector to emitter leakage current. Okay, so collector to emitter leakage current, and ICEO also depends on temperature and reverse bias voltage. The same thing for every 10 degree rise of your temperature, it is going to double. ICEO is going to double, and about the reverse bias, as we increase this reverse bias more and more will be your leakage current. Okay, is that clear? With the two of the leakage currents, so these two leakage currents are very important. They may ask you to define, or they may ask you to list the leakage currents. Two different leakage currents, they may ask you to list for 2 marks. Okay, so likewise you may get. Okay, so otherwise you may get the relation to write, or you don't have the solution for this, so you only will be asked to write the relationship between your ICEO and ICBO. Okay, ICEO and ICBO relation, they will be asking you to write for 1 mark. Okay, so the relation between your ICBO and ICBO is written so and so. Here I can write the total current IC will be equal to beta into IB. So we know that beta is equal to IC divided by IB. Isn't it or not? Okay. So now this is your majority charge carriers current plus minority charge carriers current. Okay, if I want to go for, okay. So this is your IC for all of the configuration. So IC will be equal to what? This is your majority charge carriers current and this is your minority charge carriers current. So IC will be equal to beta into IB plus ICEO. Likewise, we have for your another configuration, IC will be equal to what? Alpha into IE plus ICBO. Okay, so this is IC will be equal to beta into IB plus ICEO. Here it is IC will be equal to alpha into IE plus ICBO. So if I solve for both the things, so after solving, I will be getting an equation. What is that? It will be equal to what? ICEO will be equal to what? 1 plus beta into ICBO. So this is the relationship between your ICEO and ICBO. So ICEO will be equal to what? 1 plus beta into ICBO. So this is the relationship between your ICEO and ICBO, and this is very important. You have to remember this carefully. Okay. So this is your total current, majority charge carriers current, minority charge carriers current. Here also the total current will be equal to what? Majority charge carriers current and minority charge carriers current. Okay. So after solving this, so you will be getting the thing to be equal to ICEO will be equal to what? 1 plus beta into ICBO. So remember that carefully. Okay. So then this is all about your leakage currents. So next topic will be, next topic is thermal runaway. So what do you mean by what thing you will have in your mind after hearing thermal runaway? So thermal runaway. So something is getting spoiled. Runaway means what? It is getting spoiled. Okay. So thermal runaway, because of temperature something is going spoiled. Okay. So here we are talking about transistor. So in your transistor, if your collector current IC increases, what happens? So when we have this collector current, means current to the transistor is called collector current. Isn't it common? Okay. Collector current is going to increase. If the collector current increases, so this increase in the collector current will increase what? This will increase the junction temperature. This will increase what? The junction temperature. Okay. So when this junction temperature increases, so this junction temperature will increase the leakage current ICBO for this particular configuration of the transistor. Okay. So when IC increases, that will increase the junction temperature. Because of this junction temperature, we know that ICBO will increase. ICBO will increase. Because ICBO has increased, again IC will increase. Because we know that IC will be equal to what? ICBO. Isn't it or not? Okay. So IC has increased. Because of this increase in your collector current, junction temperatures will increase. So the junction temperature increase will increase the leakage current. We know that in semiconductors, as we increase the temperature, it will give out more and more charge carriers, and the current carrying capability will increase. Isn't it or not? Okay, more and more current will flow when we increase the temperature. Isn't it or not? Okay. So because of that, so when we have this IC which is increasing, that will increase the junction temperature obviously, because more and more charges will be moving, junction temperature will be obviously increasing. Okay, IC is increasing, that will increase the junction temperature. Because this junction temperature has increased, leakage current will be a little more. Okay, so that will ICBO means leakage current will increase. So this increase in your leakage current will increase the collector current again. So because again the collector current has increased, this will further increase the junction temperature. This further increase in the junction temperature will further increase what? ICBO, and this will again increase what? IC. So this is going to be a cumulative process. Cumulative process we will call it as, okay? Cumulative means because of rise in one thing, the other thing will increase. Because of rise in this thing, the next thing will increase. Because of this, again the first thing will again increase. Okay, so this is going to be a cumulative process, and this will happen to be continuous process. And if it happens continuously and the junction temperatures will reach reach to some maximum value. Okay, the junction temperature will reach to some maximum value. After this maximum value, the junctions will not be there. Okay, they start burning. Okay, so this is going to happen, and this will be a cumulative process, and this process happens to be continuously if it is happening. So then if it crosses the maximum junction temperature, so then the junctions of the transistor will burn out and the transistor will go spoiled away. Okay, so this will go, transistor will go spoiled, and that is what is called as what? Thermal runaway. So this is called as what? This process is called as what? Thermal runaway. It is defined as what? Self-destruction of your transistor. Self-destruction is what? Your transistor is destroying itself. Okay, so transistor is destroying itself. So because of the temperature or the junction temperature has crossed the maximum value, and this is how we have this thermal runaway which is going to happen. Self-destruction of your transistor because of the rise in junction temperature, or we can say the collector current and the leakage current (CBO). So this is called as what? Thermal runaway. Okay, so self-destruction of the transistor because of the increasing the junction temperature beyond the maximum value, and the ICBO we can say it as. Okay, so self-destruction means the transistor is going to get spoiled, and the process will make the transistor get spoiled, and the transistor will not be of use further. Okay, so that is called as what? Thermal runaway. We shouldn't we shouldn't let our transistor to go to thermal runaway. Okay, so this is how I can one can go for this thermal runaway, and this will be this is a very important question. Okay, so they may ask you for 1 mark or 2 mark to define some thermal runaway. Okay, so you have to be very careful about this topic. Okay, so self-destruction of your transistor because of the increasing junction temperature and the leakage current. Okay, so next coming to what? Stability factor. Stability factor S will be calling it as. Okay, stability factor is nothing but the ratio of what? The collector current, or change in the collector current, small change in the collector current to the small change in the leakage current. Okay, it is the ratio of small change in your collector current to the small change in the leakage current (ICO) at constant beta value and constant VBE. Okay, so beta and VBE will be constant. Then we have the ratio taken for stability. Okay, so this is a thing which will be taken for the stability of your what we can say stability of your collector current with respect to your temperature. So this is a stability factor for your temperature variation. How much stable is your collector current? This ratio will give us what? This is a ratio of what? Small change in your collector current to small change in your leakage current, and larger the value of S implies that the circuit is exhibiting what? Thermal instability. So lesser the value, your circuit is what? Stable. Larger the value of S, that implies what? The circuit is what? Unstable. Okay, so this is how we can make out this stability factor S so and so. Stability factor S will be equal to what? Delta ICO by delta ICO. So ICO is what? Your leakage current. Okay, so this is nothing but your stability factor, or the thing which will be considered because of the temperature variations. Okay, so how much stable is your collector current will be measuring with this stability factor. Okay, and finally coming to heat sink. Heat sink is nothing but it is a device. So you have seen this heat sink. Okay, so in our first year classes we have seen that regulator ICs. Over to that regulator ICs there used to be a small metal part which has been connected to the regulator IC. What it is? So that is your heat sink. So it is the device which has been connected to the component to absorb the unnecessary heat, and to safeguard the device. Okay, so as this temperature is going to increase more and more, the device will be in danger, isn't it or not? So it is a device which will be connected to any of the component to to absorb unwanted heat, to remove unwanted heat and give out the heat to surroundings. Okay, so it will be giving out the heat to surroundings, means it will increase the exhaust area. Okay, so it will absorb unwanted temperature and unwanted heat it will be absorbing, and it will be giving out to the surroundings, and thus the device will get cool. Okay, so that device which will be connected to any of the component is called as what? Heat sink. Okay, so this safeguards the device against the temperature and heat. Okay, so this is how the device will be safeguarded. So that component or that device is called as what? Heat sink. Okay, so this is also again very important definition for your 1 mark question. Okay, so thermodynamic heat sink, they will be asking you for 1 mark. Okay, so stability factor also is very important. Okay, so all these things about your chapter 2, and this will finish your second chapter, and we will continue with the next topic, okay, in the next class. Thank you.